I have the following question for you today. What is continuity correction and why do we use it? Hello, welcome back to the Quant Class YouTube channel. As we mentioned in the opening of this video, there is this idea of continuity correction. So let's give a rough definition of it first, and then we can discuss why we use it. So if we consider this discrete distribution on the left, we can only take on values where we have those vertical lines, right? And we can't fall in values in between. Whereas if we look at the continuous distribution on the right, we don't really consider falling on one particular value. Instead, we consider what's the likelihood of falling into a range of values. Continuous distributions, such as the normal distribution, are often easier to work with than discrete distributions, such as, say, the binomial distribution, Poisson distribution, or numerous others. And ultimately it's a matter of the fact that discrete distributions often involve summations, and summations can be quite tedious and time consuming to calculate, as well as resource intensive. Now, we can't just jump from the discrete distribution to a continuous distribution. Because of what we mentioned earlier, the probability of, for example, falling exactly on this red line in a continuous distribution is 0, right? Because the area of the line is 0. And to account for this difference in behaviors between continuous distributions and discrete distributions, we pretty much adjust the probabilities a little bit. And that's the rough idea with continuity correction. Why do we use it? As we alluded to earlier, many continuous distributions, such as, say, the uniform distribution or the normal distribution, are a lot easier to work with than their discrete counterparts. So let's look at a particular example. One very common application of this is approximating the binomial distribution with a normal distribution. So, as a refresher, the general idea with the binomial distribution is this. We have 3 variables that we're working with here. N, our number of trials, P, our probability of success, and K, the number of successes. And in general, a binomial distribution is used to model situations where we have only 2 possible outcomes, and we have a fixed number of trials. When we have such a scenario, our probability mass function is given by this formula here. N choose k times p to the power of k times 1 minus p to the power of n minus k, where again n is the number of trials, p is the probability of success, and k is the number of successes. And to get to our CDF, or our cumulative distribution function, we sum the values of our probability mass function from 0 up till whatever value k that we want to know about. And 2 other pieces of information that will become relevant are that you can determine the mean of a binomial distribution by doing your number of trials times your probability of success. And your variance is given to you by your number of trials times your probability of success times 1 minus your probability of success. So let's look at a particular example. In this example, let's just say we're considering a particular program. Let's just say it's some government program. And let's say that 60% of applicants qualify for that program. Out of 50 applicants, how likely is it that 5 or fewer applicants qualify? So let's parse out the information on this problem. We have P, or our probability of success, as being 0.6, or 60%. We have 50 trials, and we care about K being equal to 5, right? Because we want 5 or fewer to qualify. So we can determine this by calculating the following sum. I equals I equals 0 to 5 of 50 choose I times 0.6 to the probability of, to the power of I, times 1 minus 0.6 to the power of 50 minus I. And in this particular example, we're working with a small enough sample size and a small enough number of successes where it's not completely impossible to calculate this. using a software tool, I'm getting that this value is approximately 2.196 times 10 to the power of negative 13. Now, let's consider an example of our normal distribution. So our normal distribution is a continuous distribution, and the main concept of the normal distribution is that we have our mean at the middle, and we consider distances both in the positive and negative direction in terms of the number of standard deviations. And our z-score formula, which in general is x minus mean over standard deviation, where x is our point that we're considering, or our data point, allows us to translate a general normal distribution into a standard normal distribution, i.e. with a mean of 0 and standard deviation of 1, and that will allow us to make more fair across the board comparisons, as well as being able to accurately calculate values. So let's consider this example here. Let's say Mensa accepts candidates whose IQ is in the top 2%. If IQ is normally distributed with a mean of 100 and standard deviation of 15, does someone who scored a 133 qualify? So breaking it down, we can figure out our z-score first. Now our z-score is going to be given to us by 133 minus 100 over 15. And this turns out to be 2.2. And now we can formulate this question in terms of the following. What is the probability that z is greater than 2.2? And using a software tool, this turns out to be just about 0.014, meaning that this person scored in the top 1.4% of people, and they would qualify for Mensa. And now to jump to the idea of actually utilizing this approximation technique. If we use our normal distribution to approximate the behavior over a binomial distribution, the first thing that we want to check is effectively, do we have enough data to work with? And the criteria for that is n times p, or our number of trials times our probability of success, has to be greater than 5. And n times 1 minus p, or our number of trials times the probability of our failure, is greater than 5. Although it is generally preferred that these values actually be greater than 10 rather than greater than 5. So then we also have this concept of continuity correction. This is what we were alluding to earlier. Pretty much if the values on the left, let's just say we're considering the probability of exactly 5 successes, then when we convert to a normal distribution, in addition to figuring out our mean and our standard deviation and using our z-score formula, we are going to subtract 0.5 and add 0.5, and we're going to consider the probability of falling within that given interval. And then following suit, if in our binomial distribution, in our discrete case, we were considering the probability of x being greater than n, let's just say probability of more than 5 successes, then when we translate that to the normal distribution, we're going to add 0.5 to our data point, and then use our z-score formula. And you can see the rest of the formulas here for the rest of the different cases. So, jumping back to our example from before with our binomial distribution, we still have a probability of success of 60% or 0.6. We still have a sample size of 50, and we still care about five or fewer successes. Well, first, let's make sure that our criteria are met. So n times p, in this case, is going to be 50 times 0.6, and that's going to be 30. And this is greater than 10, and it's also greater than 5. Similarly, n times 1 minus p is 50 times 1 minus 0.6. And this is going to be 20, and 20 is also greater than 10, which means that we can use this approximation. Then from here, our mean is 30, right? Because as a reminder, our mean is given to us by n times p. And our variance is going to be given to us by this formula, n times p times 1 minus p. And that's going to be 12. So that means that our standard deviation, which is the square root of our variance, is going to be the square root of 12, or 2 square root 3. Because we care about 5 or fewer, that is this third option down here, x less than or equal to n. So we want to consider in our normal distribution x being less than n plus 0.5. The particular value of the number of successes that we have is 5. So we really care about the probability of being less than 5 plus 0.5 or 5.5. From here, if we use our z-score formula, our z-score that we're considering is 5.5 minus 30 over 2 square root 3. This, using our software tool, again becomes just about negative 7.217. And accordingly, we can again use our software tool to figure out the probability of z being less than negative 7.217. If we do that, this comes out to be about 2.660 times 10 to the negative 13th. And as a reminder, that's quite close to what we calculated before. Here it was 2.196 times 10 to the negative 13th. Now, the main advantage of doing it this way, though, is that the normal distribution is much easier to work with in terms of our calculations, and given a large enough sample size and a large enough number of successes, it can be prohibitive to try and calculate these probabilities using the binomial distribution directly because of the large summations involved. So kind of to summarize what we're discussing today, transitioning from a discrete distribution to a continuous distribution will often ease our calculations. However, when we do that, we have to correct for the fact that in a discrete distribution, we can fall exactly on a value, whereas in a continuous distribution, we consider falling in a range or interval of values, with one very common application of this being approximating the behavior of your binomial distribution with the normal distribution. If you found this content informative, please support the channel. You can do that by sharing this video, liking this video, commenting, subscribing to the channel, and just honestly sharing it with your friends and family. The farther it gets out, the more it grows. Also, if you're interested in one-on-one tutoring sessions, please follow the link in the description. Have a great day.